So we can use momentum to explain a lot of things in our life, particularly involved in cars and in car crashes. It makes sense. So we have this sports car traveling at 27 meters per second, and it can be stopped in 21 seconds by gently braking. It can be stopped in 3.8 seconds in a panic stop, which means they slammed on the brakes. And it can be stopped in 0.22 seconds if it hits a solid wall. And you know from experience that the force applied to the car, and thus to the person driving in the car who is also moving at the same speeds, is different in all of these situations. In the first situation, the force is much gentler. You feel that because you're traveling at the same speeds and are stopped at the same speeds. Your momentum is less, but the forces are comparable. So you know that it's a lot less force applied to your body when you gently brake versus where you slam on the brakes and the seatbelt hits you hard. And hopefully you don't know what it feels like to hit a solid wall, but you can imagine that it's much worse than slamming on the brakes. So we can use our impulse momentum equations to talk about how force changes with time. We know that F delta t, the impulse, is equal to the change in momentum. So for this situation, our mass is always 1295. And our first velocity, and I'm going to use 1 and 2 in this case to match our momentums, but you can use not and not to mean initial and final. So 27 meters per second. And what's our final velocity if we're coming to a stop? It's 0. And because we're not using velocity, we're using momentums, I'm going to go ahead and calculate momentum right away. We know that momentum, P equals m times v. And for these simple equations, I don't need you to show me the work unless you want to. So we have mass times our initial velocity. So our P1 is equal to 34965. And it's got momentum units, kilograms times meters per second, because we did kilograms times meters per second. And our final momentum is always 0. And we have 3 different situations. We have our gently braking, our panic stop, and our hitting a solid wall. And we're trying to find force with this time. So we know we can rearrange this equation to tell us that force equals P2 minus P1 divided by the change in time. So we can look at all 3 situations. When we are gently braking, so gentle, our time is equal to 21 seconds. So we can calculate our force, P2 minus P1. And for all 3 situations, the change in momentum is going to be the same. It's going to be this negative 34,965. Divided by our time. And you get negative 1,700. And if we look at our units, we get kilograms times meters per second squared, which is called a Newton. So this is our force. The negative sign just means it's in the opposite direction of the initial velocity, because we assumed this was positive. So that's a good amount of force, but it's a large car. So let's look at the next situation, where we have a panic stop. and our time is 3.8 seconds. So we know our force is going to be equal to our change in momentum divided by our time. And we know that this is going to be 9,200 newtons. And again, it's negative direction because it's opposing the original motion. And let's do the very last example when we hit a wall. When our time is a tiny fraction of a second. And it is 160,000 newtons. And that's a pretty huge increase between these two. And it's a pretty big change in time as well. But this makes sense to us intuitively. If you take a really short time to stop something, then it's a very large force versus slowing it down quickly. You can even think about this when you were swinging on swings when you were a little kid. If you started dragging your feet to slow yourself down, it didn't take a lot of force. But if you jumped off the swing and jumped onto the ground, it was a lot of force on your body and in your feet to stop your motion quickly. This is also why we wear seat belts. Because if you think about it, when you're moving forward in a car, when you slam on the brakes and you move forward, your seatbelt moves a little bit with you, so it makes it take a little bit longer for you to slow down. Versus if there's not a seatbelt there and you hit the steering wheel, you're going to stop in a fraction of a second. So the force would be a lot greater on you.